In the last two modules, we examined drives and their specialized I/O devices, encoders. It's now time to move on to examining input-output devices in general. They're the third pillar of industrial automation and a very important one. Without I/O devices, controllers and drives couldn't monitor their environment, nor could they issue or receive commands. This topic is very broad and complex, so we're going to focus on the highlights rather than trying to be exhaustive. Let's get started. Input output devices provide the control and status information that flows between the application and its controlling devices. As I mentioned back in Module 1, I/O devices are the application's arms, legs, and senses. And just to make things crystal clear, the device's direction, whether it's an input or output device, is based on the controlling device. This VFD, for example, is a controlling device. It has a selector switch, potentiometer, and two push buttons connected to it. These are input devices because the VFD inputs information from them. On the other hand, these indicator lights are output devices because the VFD outputs information to them. Let's define three important terms before going further. A sensor is an input device that detects or measures a process's condition. In many applications, sensors are the most numerous I/O devices. They provide crucial feedback that controlling devices use to make decisions and maintain safe operation. An actuator is an output device that produces movement. Drives are actuators, so technically they're output devices. But since they're so important, we usually treat them as a separate category. Many other devices produce movement, however. Solenoids and valve actuators open and close valves. Linear motors, as well as electrically controlled pneumatic and hydraulic devices, are actuators as well. And finally, a human machine interface, or HMI, is a device that facilitates sophisticated interaction between a machine and its operator. An HMI is a lot more than a button or light. In most cases, it's a full color graphical touchscreen that provides custom controls and displays. Machine operators use HMIs to control applications and monitor their operation. I/O devices come in vast variety and have many purposes. I'm not exaggerating. There are so many I/O devices that it's a little daunting to cover them in one module, so let's classify them to keep things manageable. First, we'll divide them into three broad categories: input devices, output devices, and complex devices. Input devices split into two more categories: control devices and sensor devices. A control device makes something happen, like a machine's start button. Sensor devices report information, like a box on a conveyor passing the sensor. These two categories in turn divide into two subcategories each: digital and analog. A digital device communicates with on off signals or with numbers, usually in binary form, zeros and ones. These simple signals can do a lot, as this module will demonstrate. An analog device, in contrast, communicates with a smoothly varying voltage or current signal. Analog devices are common when the application includes equipment that must be opened, closed, or moved smoothly and gradually. Output devices split into two categories: actuator devices and status devices. An electrically controlled valve is an actuator output device. Status devices report information to the machine operator. A fault indicator light is an example. Like control and sensor devices, actuator and status devices also come in both digital and analog forms. Complex devices usually perform both input and output functions. Complex devices divide into smart devices and HMIs. Smart devices contain their own tiny controller, and many communicate over an industrial network. Both smart devices and HMIs generate digital data streams that they use to communicate with other devices. A digital data stream is a flow of binary bits, zeros and ones, arranged in groups called packets. In the last module, you learned about Movilink DDI encoders. These are smart I/O devices that communicate with the VFD using a digital data stream. Okay, let's drill down into input devices by looking at some examples. Common control devices include push buttons and toggle switches to start, stop, activate, or deactivate equipment. Selector switches choose between options. Keypads let the operator enter numbers into the application. All these devices are digital. Selector switches and keypads usually output a binary number rather than a single on-off signal. Potentiometers are analog. They let the machine operator smoothly control the machine's speed or position by turning a knob. Common sensor devices include photosensors and proximity sensors that monitor moving objects on a conveyor. Limit switches are safety sensors that halt the application if something moves outside its legal limits. These are digital devices that turn on or off to signal an event. The temperature probe is analog, outputting a voltage or current signal that corresponds to the temperature. It's time for a few output device examples. Common actuators include valve solenoids and relays. When triggered by a digital signal, the valve solenoid opens or closes a valve, while the relay opens or closes an electrical circuit. The gripper snaps open or closed in response to a digital signal. The valve actuator, however, is analog, smoothly opening or closing in direct proportion to the voltage or current signal entering it. Indicator lights and signals are the most common status device. They turn on or off in response to digital signals. Similarly, alarm devices react to a digital signal, alerting operators of problem conditions or dangers. Numeric displays are slightly more complicated output devices, requiring a binary number that they translate into the corresponding pattern on the display. Finally, let's look at a few complex device examples. Many instruments that the chemical industry uses to monitor pressure, temperature, flow, and fluid levels are smart. Similarly, smart valves open or close by specific percentages in response to a command over their digital data stream. And powered rollers used on conveyors have their own smart controller that accepts commands and reports their status to higher level controllers. Many HMIs have color touchscreens, but some have simpler LCD displays with an attached keypad. And some color keypads attached to a compatible VFD, acting both as an HMI and as a configuration tool for commissioning and diagnostics. I think you have the big picture. Now let's look at a few more details. Simple digital devices, which have just one input or output, respond to or generate a low or high signal. The low signal has a voltage close to ground, 0 volts in other words, while the high signal has a voltage close to positive 24 volts DC. These voltages don't have to be dead on, but they need to be reasonably close to these values if the device is to work properly. Also be aware that equivalent terms for low are off, 0, and false, while equivalent terms for high are on, 1, and true. Okay, let's examine some simple digital I/O devices in action. Toggle switches output a low or high signal depending on their state. This single pole double throw switch is connected to a positive 24 volt DC power supply and ground. The common terminal acts as the output. Notice what happens when you flip the switch. The voltage goes almost instantly from around 0 volts to 24 volts. When you flip it off, the voltage drops back to 0 volts. From a digital perspective, the output changed from low to high and back to low. Pretty simple. Push buttons come in two styles: normally open, NO, and normally closed, NC. The red button is NO, while the blue one is NC. Normally open push buttons output a low when unpressed, while normally closed output a high. When pressed, the push button outputs the opposite value. Notice that when we press the red button, its output goes high, while pressing the blue button makes its output go low. When released, the output returns to the original value. Notice that when we release the red button, its output goes low, while releasing the blue button makes its output go high. Normally open devices are also called active high because they go high when you activate them. Similarly, normally closed devices are called active low since they go low when you activate them. Most digital sensors behave like switches and push buttons. They're either normally open, active high, or normally closed, active low. For example, this conveyor has multiple beam brake sensors that detect boxes as they pass in front of the sensor, breaking the light beam. These sensors are active high, so their outputs are all low right now since nothing is breaking the light beams. We'll put a box on the conveyor and start the belt moving. Watch what happens to the sensor outputs. As you can see, when the box breaks the beam, the output goes high until the box passes by, at which point it goes low again. This overhead conveyor moves car body panels to different stations. It includes two limit switches with active low outputs to prevent the travel drive from moving too close to the ends of the rail. Both switches are high because nothing is touching them. But if the travel drive moves too far and touches the right switch, it goes low, triggering an immediate stop. As I've already mentioned, some digital devices have multiple outputs that combine to form a binary number. Each output line's low or high value becomes a single 0 or 1 in the number. A multi-position selector switch is a good example. Notice that it has 8 positions, numbered 0 through 7. It has 3 digital output lines that form the binary number. We call this a 3-bit binary number since it contains 3 zeros or ones. When the switch is in the 0 position, all 3 output lines are low, so the binary number is 0, 0, 0. As the switch rotates to each successive position, notice that the pattern changes to the binary numbers for 1 through 7. If you're new to binary numbers, pause for a moment and see if you can figure out how the patterns for each value change. And if you're still confused, I suggest you watch one of the many excellent binary number tutorials on YouTube. Digital actuator and status devices activate or deactivate in response to low and high signals. An active high output device activates with a high signal, while active low devices activate with a low signal. Pretty logical. This indicator light is active high. Since the input is low, it's not illuminated, but change the input to a high and it lights right up. Go back to a low and the light goes out. This motor brakes controller is active low. Right now, the input is low, so the brake is holding the motor in place because braking is its active condition. Make the controller's input high, however, and the brake releases. But as soon as that input goes low again, the controller slams on the brake. Automation engineers choose a device's active level with care. The device should never activate unexpectedly if something fails. Devices that affect safety are often active low, so they enter a safe condition if something fails, power is lost, or a wire is cut. The break that we just looked at is a good example. If a break with an active low input gets disconnected accidentally, the break automatically engages. That's a safe thing to do. If the break were active high instead, accidentally disconnecting a wire would cause the break to release unexpectedly. And if that break were keeping a loaded hoist in the air, the load would suddenly plummet to the ground. Not good. On the other hand, devices that initiate operation are often active high, so if something fails, power is lost, or a wire is cut, nothing happens. For example, if the power attached to a machine's active high start button fails, the machine won't start when the operator presses the button. Annoying, but harmless. If the button were active low, however, the machine would start unexpectedly if the power attached to the button fails. Yikes, bad idea. This design philosophy of ensuring that equipment behaves safely during a failure goes by the name failsafe. Now let's look at analog devices which behave quite differently from digital ones. Analog devices generate or respond to a continuously varying voltage or current signal. The device's response is proportional to the signal's magnitude. Common analog voltages range between 0 to positive 5 volts DC, 0 to positive 10 volts DC, negative 5 to positive 5 volts DC, and negative 10 to positive 10 volts DC. The most common analog current range is 4 to 20 milliamps. Let's examine some analog I/O devices. Potentiometers are analog input devices. They're rotary controls whose electrical resistance changes as you turn the knob. When connected across a power supply, they output a voltage proportional to the knob's position. This potentiometer is connected across a negative 5 to positive 5 volt DC power supply. When the knob is in the middle of its range, the output is 0 volts. Notice how the output voltage varies as the knob turns, first counterclockwise and then clockwise. Potentiometers often serve as manual control devices. This Movimod Advanced VFD has a hand control box equipped with a potentiometer. Turning it changes the VFD's speed set point, which alters the motor's speed. A voltage controlled valve is an analog output device. It moves proportionally to the voltage entering it. This valve accepts an analog signal between 0 and positive 10 volts DC. When the input voltage is 0 volts, the valve is fully closed. As the voltage increases, the valve progressively opens. As the voltage decreases, it closes. I/O devices directly attach to most VFDs and controllers. For example, this MoviDrive technology has 8 digital inputs, which we usually call DIs. It has 4 digital outputs, or DOs. If you install a CIO21A expansion card into it, you gain 4 more DIs, 4 more DOs, plus 2 analog inputs and 2 analog outputs. PLCs can control a variety of I/O devices depending on the I/O modules installed. This PLC has 4 I/O modules, which give it 32 DIs and 32 DOs. Standalone I/O modules can attach to a field bus, an industrial network, which makes them accessible to any device on the network. Networked controllers and PLCs can access attached I/O devices through the network. For example, this UHX86A controller and these two I/O modules all communicate over an EtherCAT field bus. The controller can monitor attached input devices as well as control attached output devices. Many complex devices like HMIs and smart instruments connect to other devices through a field bus rather than directly. For example, this PLC, laptop, UHX-45A controller and a WAP11D HMI share a common industrial Ethernet network. They can exchange data efficiently through their various digital data streams. And that leads us, rather neatly, to our next module's topic, controllers and field buses. We'll see how they tie everything together and orchestrate applications through automation control programs. Since this module was a pretty hefty one, I suggest you take a break and have some coffee first. See you next time.